Now, if we take low spins, and we bound it, we get 32 pi, which comes from 16 pi times 2 times this 2. S minus 4m squared have sum to L, have 2j plus 1. We have the integral 4m squared over s ds prime. So this is, you see what happened is that here we had the formula which was a square root. Now we bounded this guy by the, if you set z equals 4, here it's an inverse square root, so square root cancels. And then 2 is left here, so let me write it. 2 times 16 pi. And we are left with the integral. This integral simply cancels this s minus 4. And we got that low spins are bounded by 16 pi, L plus 1, L plus 2. This sums is this sum. Any questions about that? Sorry? Oh, yeah.
Like the low spin contribution diverges in 3D, right? From this estimate.
The low spin contribution diverges in 3D.
Yeah, suppose d is equal to 3, then the imaginary part of fj grow as square root s, then if we take the average, it will.
So yes, and j will be different than d equals 3. And okay, let me say you this. So yes, so maybe you would like, first of all, maybe you would want to start with some different averaging to simplify it in d equals 3, but it doesn't matter. If we started here, I don't know on top of my head what is this factor here. And this integral, whatever it is, it cannot diverge because it's just finite everywhere on the integration region. So at 4m squared, you have square root, and here you just have a constant in d equals 3. So it will be finite. At upper level, okay, you might get some dependence on s. So you might get some s here times s. That's not a problem. So there is no divergence here. Yeah. It could depend on s maybe in d equals 3, but yeah.
Yeah, I guess it depends on s in every dimension, different from 4.
Yeah.
But is there anything interesting to say in different dimensions about the s dependence? Like, I guess in higher dimensions it will be down by powers of s, and in lower dimensions it will be up by powers of s.
The final bound will be completely homogeneous along dimensions. So this is just a one term, right? It's just low spins. We are not. We are trying to bound the total cross section, and we are now have bounded low spins. Then we will have to bound the whole thing, and when we bound the whole thing, the dependence on dimensions will be smooth.
I see, but that's not obvious from.
It's not obvious yet. Yeah, maybe from what I said, but that's fact. Any other questions? Okay, so far what we've done is that we use unitarity to get the estimate for the low spins. So now we come to the tricky part, or tricky part of the proof, which is that we need to get handle on this higher spin part. And remember previously, when in the last time, when we talked about it, we did this toy model where we say, well, at large impact parameters, something happens that we expect, and this large impact parameter behavior is exactly related to high spins. So we use that to estimate the tail, but now we will use it differently.
Sorry, Sasha, can you remind me if this also works for theories with massless particles?
So far,
like what you've done so far.
So, okay, there are a few things I have to say. Yes, well, let me just add it here. So massless particles. So first, if you want to use partial waves, which I used here, they converge pointwise for d larger than 7. So if you take, for example, gravity, and it's related to collinear pole, if you take a gravitational theory in d larger than 7, then so far everything I said it makes sense. Also in d larger than 7, there are no IR divergences. Now for d between, say, 7 and 5, it just does not make sense because in gravity total cross section will be infinite. If you take this total cross section, I think it will diverge because of this, effectively because of the graviton pole. Well, and finally in d equals 4, there are IR divergences, so I do not know how to proceed with, at least all the formulas have to be modified to address the states. But otherwise, the basic argument is the same. So far, everything I've written, you can apply to gravity. You just set m to 0, set d to equals to 8, for example, and that's fine. Oh, graviton pole is just if we have two particles, they exchange a graviton, then it's has a pole 1. The amplitude behaves like 1 over t, right? T is 1 over 1 minus cosine square. So then if you take unitarity, then for the, well, let's take the amplitude at low energies, at short angles, at small angles, it behaves like 1 over theta square. Now, if you take imaginary part of an amplitude and you try to set t to 0, by unitarity you get the integral of the type, I think, d theta. Remember, unitarity was imaginary part is equal to t square integrated over phase space. So we have to remember what the integral over phase space is. It's d theta. Here you have, I think, theta something like d minus 3 over 2, or maybe it's just d minus 3. I don't remember. Here you have amplitude square. So you have 4, and then you just have d larger than something. For this integral to converge, that's it. I will add it to the notes. Now here comes a crucial thing where you cannot apply to gravity, and where the so far everything I said is not sensitive. Now what I will say is really applies to gap theories. And here we use the second ingredient, which is polynomial boundedness plus analyticity. And more precisely, it is in fact analyticity for t strictly larger than 0. So remember last time we ended with Martin's extension of a Lehmann ellipse. And the crucial point about Martin's extension was that the amplitude is analytic for t, which can be strictly positive and does not depend on s. And it is polynomially bounded also for these values. So this is a crucial insight or crucial result of a lot of analysis. And what does it mean in terms of formulas? It means that they exist in such, say, an integer n, such that this following integral is less than infinity. So this is what it means for an amplitude to be polynomially bounded. If we take it on the real axis, we take some t naught which is positive, and we choose some n which is large enough, the integral converges. Does it make sense? Okay. So now let me just comment, because it might sound a bit abstract. But this T0 will be related to the size of the object. It's not clear now, but it will be clear later. So this T0, it comes formally from the region of analyticity, but it is related to the size of our objects. It will become clear later. So for now, it's just that such positive T0 exists, and then the final bound will depend on this T0. Now, I guess I focus on the scattering of identical particles, and let me set T0, which is, let me say, now focus even on scattering of pions. And for pions, T0 is equal to 4m pion square. There is a slight wrinkle here, or maybe subtlety, that maybe it's minus epsilon here. But let me ignore this, so just set 4m square. But let me emphasize again that any T0 will do. Now, here is what you need to know about Legendre polynomials. So consider Legendre polynomials, and the same thing is true for Eigenbauer polynomials. This Z is related to T and S like this. So you remember that now, and now you see what happens. If S is larger than 4 and T0 is positive, let's evaluate it at T0. This argument is larger than 1. Both of them are positive. And here's the fact that is crucial, that if you take Pj of Z, so first of all, it's positive for Z larger than 1. And also, it's an increasing function of spin, and it's an increasing function of Z. You can just open Mathematica, plot Legendre's, and check these claims. That it grows with J, it grows with Z, and it's positive functions when Z is larger than 1. When angle is between -1 and 1, so this is related to cosine angle. So when Z is between -1 and 1, of course, they oscillate. But in this regime, when T0 is positive, they just grow. So let's now plug in this formula partial wave expansion. So what I do now is I plug into this formula the definition of this thing. So it will be sum from 0 to infinity, 2j plus 1, 16 pi, imaginary part of fj s prime. And here we have Legendre polynomials. Evaluated, if I set T0 to 4m pi square, we evaluate it at 1 at T0. So set T0 to 4m pi square, so we get 4m pi squared. And you see now why it will never work. It will not work for massless theories, because in fact for massless theories, you know you should have a cut. For gravity, you have a cut starting at T0 equals to 0. So if you have a graviton, because you can produce gravitons, you have a non-relativity in T starting from 0. So this is not true. Here where the theory is gapped. Now, now we do the following thing. First of all, note that these guys are non-negative, shown here. These guys, I told you, are also non-negative. Therefore, if we want now to, I can bound this sum. This is an equality. But if I drop few of spins, I can write the inequality. This is larger or equal, and here I can write starting from L plus 2. So I simply use the fact that each term is non-negative. And now we use the second thing. We have an integral here from 4m squared to infinity, and each term is manifestly non-negative. Therefore, if I'm interested in the bound, I can chop this integral here as well and put here s. Fair? Fair. Now, let's proceed. If we are interested in simply bounding this object from above, you see that we are dividing by s prime, and n will be some positive integer, say. Then if I want to bound this object from above, I can pull out this s prime because it's maximal on the upper limit. So I can evaluate it on the upper limit. And I write this. We erase this thing. Now, the next step, we can also take this Legendre polynomial and also pull it out by evaluating it on the upper limit. Because you see, so this here s prime, when s prime becomes bigger, the argument becomes smaller. And I told you that these are increasing functions of the argument. So if we are bounding from above, we can pull it out as well and evaluate it on the upper limit. So we get pj 1 plus 8 square over s minus 4 n squared. And now we are left almost with the sum which we want here. It's from L plus 2 to infinity, these things, and j. The only thing that we're missing is this, but it's also easy to restore. So we just, again, you can check. We're bounding from above. I can divide and multiply. So I multiply by this, and I insert here and you can check that this product is always less or equals than 1 in this interval. And therefore, you see that now we got here this part is what we called high spins. And we got that high spins are bounded. So this integral and all these things, they are bounded so high spins are bounded by an, some number. And here we have P. One important thing that you didn't catch my hand. You see here I'm summing over j. So if I pull out something out of the sum, it cannot be j. And here yes, it should be L plus 2. And I'm using the fact that it's an increasing function of j. So I take the minimum spin. Every guy can be only bigger. So if I'm bounding from above, I can take the minimum spin. Yes, so here it's L plus 2, 1 plus 8 m pi squared, s minus 4 m pi, just call it m squared. And well, here we have s n plus 1. And here we have also the square root. So this was the crucial step. We bounded high spins using gap, analyticity, partial wave convergence, and polynomial boundedness an is less than infinity. So now let me update this formula based on what we've done.
So the reason that you needed to look at high spins is because you want a large damping factor in the denominator? I mean, in principle, you could just do the entire sum, right? The bounded sum.
How would you do the sum?
I mean, I can always lower L in your sum, right?
So we would like to bound this sum from L to infinity in terms of something which is finite.
Yeah, but in principle, you had the sum from 0 to infinity, right?
Yes, so I split it in two.
You split it in two, and I guess is the reason that you split it in two is, of course, the higher the L where you split, the stronger the bound, and for some reason you need that.
There is an optimal L. We will optimize over L.
I see.
Yeah.
So if you took it from 0 to infinity,
yeah, you will
get
just
a bound, but
it will be useless. Yeah. So at the moment L is a parameter, and then we will optimize over it. So at this point, let me rewrite now this equation. Yeah. Yeah. So let me repeat why I need a gap. So the logic is the following: we take an amplitude, and we look at its region of analyticity in T. And by standard theorems, if you have a region of analyticity, if you have ellipse, you have a convergent partial wave expansion. If you do not have analyticity, you will not have. Yeah. So this is low spins. And there is a high spin. So far I only used things which you can. Well, this maybe you didn't know, but if you can easily see it, now I will use the only step, which is slightly maybe unfamiliar, and this is the following inequality. Again, I don't know the exact history, but I guess, again, it was Martin who found it or used it. So there is this following fact about Legendre polynomials, that they are bounded from below by the following thing. Here, it's important that z is larger or equals than 1. And phi 0, it's up to you. You can choose it between 0 and pi. So this, again, just you can check. This is a fact about Legendre polynomials. And using this, you can, you see, again, if we are bounding cross-section from above, and the Legendre polynomial stands in the denominator, and we are bounded from below. Therefore, we can apply this bound from below and plug it here while keeping this. Is it clear? You know, if we are dividing by a bigger number, we're getting something less if we're dividing by a smaller number. Therefore, the next step is just apply this inequality here. And at this point, let me make a simplifying assumption, and then we will check. Well, first of all, I would be interested in S much larger than 4m squared, so large energies. And second, let me make an assumption that L is much larger than 1. And then we will see that it's much larger than 1. It will be just self-consistent. It's just a simplifying step. It's only algebraic step. So then you can check that this inequality, and if you simplify it a bit with this, I wrote it in the notes, it allows you to rewrite this guy as follows. Well, it's this, instead of this Legendre polynomial, this of course all stays. You get pi over phi naught. And here you get 1 plus 4m square root s cos phi naught to the power minus L minus 2. And this is a crucial thing, that you see that this guy, this is slightly larger than 1, and this decay exponentially with spin. So the contribution of high spins is exponentially suppressed in spin. And here we go. We got this bound. And so again, if L is much larger than 1, let me, instead of this L plus 1, L plus 2, just write L square. So now I have to put some quickly line. So we have low spin gives this, and high spin gives this. And again, at high speed, at high energy, this is just 1. So you can simplify it as well. Just 1. And yeah, there was some maybe averaging that I missed, some extra factor. So good. Let me just rewrite this bound after simplification. So that's we're almost there. Now we are coming back to Monica's question.
This
Yeah.
phi 0, they satisfy that bound for some phi 0?
For all phi 0 between 0 and pi, it's a free parameter. For
So
every.
if I take it to be pi over 2?
Hmm?
If I take it to be pi over 2?
Okay, then it's not the best choice. Because this will be 0, right? So this will be exactly 1, and it's not suppressed at large L.
I see. So you're also
Phi 0 we will choose. Let's yes, but
you're optimizing with respect to both.
yes, we will optimize with respect to both. Yeah. So let me optimize with respect to L, and you can take it as an exercise. That if you just take a derivative and set it to 0 at large S, you get that the dominant spin is n minus 1 square root S log S S naught. You can put any S naught you want. The leading order, it's log S what matter. And here you have 4m cos phi naught. And now you plug it back into this formula. And here you go. We got that the average cross-section is less or equal than 16 pi s n minus 1 log s over s naught for m cos phi naught to the square. So this is a bound. Let me comment on that. So again, remember that this was the average cross-section. So if you don't want to discuss average, you can just naively drop this s, and you get the famous log square bound, but this is a bit more careful. Now, there are several things here, several wrinkles, which you might be unhappy with. First, when I was taking s, yeah, and you see that for large s, this L star is large. So this is right, because it's grows with s. So there might be few wrinkles with which make you unhappy. Is that first, okay, I still drop this +1, +2 because L was large. Of course, it's all small corrections as you expect. But there is this n, there is this phi naught, well, phi naught we would like to set to 0 clearly here to make a best bound. Then there is S naught. So how do we, and finally I took S to be large. How do I apply this bound to, you know, the cross sections that we observe in the experiment? So this is not completely yet a good bound, but the claim is that all these wrinkles you can just iron out and you get a precise bound. So let me write it.
Sorry, so in whatever experiments you're talking about, what is large S?
Yeah, so
than M, or you have other stuff?
In fact, you can derive this kind of bound for any S, for finite S. So any energy you have, you can have a bound which just, you can have a finite S bound, which at large S becomes this. So yeah. Oh, well, the question is where is dependence on AN, and of course it should be there. Yes, my L star should depend on AN. Yeah. Sorry? It might be hidden in a 0, but I have to check. It might be hidden in a 0. I think it might be that the dependence on it is subleading, and so it's hidden in a 0. But yeah, I think in fact the log S here does not depend on it. So okay, so let's just go through this. First of all, and that was how it was done. After you derive this bound, remember we start with polynomial boundedness for arbitrary n. We said the amplitude is polynomially bounded with arbitrary n, but now after we derive the cross-section bounded by s log s square, you see immediately that for negative t, because from positive Legendres, so here the Legendres do not oscillate because t equals 0. So if you go to negative t, because you have this inequality, the amplitudes cannot grow faster than that. And this leads to the fact that, in fact, the polynomial boundedness for relativistic amplitudes comes with, at most, 2 subtractions. So n equals to 2. And again, the reason, so you first start with arbitrary n, then you use unitarity, and then you use unitarity again, and you realize that, in fact, n can be at most 2. Again, the argument is just we started with arbitrary n, we derived this, and from this n equal less than 2 follows. And then, well, you set n equals 2, you set phi naught to 0, and then you get the bound which you often maybe see, or you will more often see in the books, that it is like this. Again, it's the average cross section. That's why you have it S, this S here. And if you want to see the bound without S naught and at finite S, I just inserted it in the notes. It's just a formula which goes essentially through the same argument, and then you can apply it to the your favorite experiment. Now, at this point, let me make a quick recap of remember last time we discussed analyticity and its extension by using unitarity. So at this point that we derived this bound, let me recap the basic things you should remember from all these discussions.
So, Sasha,
Yes.
just a quick question.
Can I ask a question?
Please. Question from online?
Yeah, yes.
Yes.
Hi, Sasha.
Hi.
So from this proof that you presented, it's kind of clear, basically the moment you said that these Legendre polynomials are positive and they behave monotonically, it's kind of clear already from this moment on that you are going to get some bound. Okay, it's just, okay, you have to do the algebra, but it's obvious that something's going to happen and it's going to be interesting. So from this point of view, it's clear that the main mystery is that how the hell Martin argued that there's going to be this analyticity up to T0, which you showed. So the rest is algebra, basically. So that's the most non-trivial thing. And can you give some intuition, how did he perform this analytic continuation? Did he have some integral formula that expressed the amplitude for, or what exactly did he do? Because that seems to be the only non-trivial thing in the whole business. The rest is just some algebra.
Yes, that's right. It's a crucial step. So let me say a few words now, and next time maybe I'll be more precise. But the basic idea, I think, is that he starts, the way he does it is that he starts with the dispersion relations with finite number of subtractions. And this dispersion relation can be either dispersion relations like the first dispersion relations were derived. They didn't have any, they just had the simplest cuts and no this potato-shaped region by Bros, Epstein, and Glaser. But the claim is that it doesn't matter. You can start with dispersion relations with or without this potato. So you write it for negative t. And then you write partial wave expansion there. And then you start, I guess maybe one of the key steps is that we would like to start differentiating this dispersion relation and with respect to t around t equals 0. And using unitarity to show that in this way we get some series expansion of an amplitude around 0. And my understanding that what he managed to show is that he put an upper bound on these derivatives using unitarity. And then he argued, I guess, that you can resum and you have some finite radius of convergence in T. Now, I would need to next say, if I start with dispersion relation and the crucial thing is, of course, as soon as I wrote dispersion relation, that's fine, that was just QFT. But then as soon as I inserted there the partial waves, and I use the partial waves, each of them are bounded from below, then it seems like at this step, okay, if I start with dispersion relations, I haven't explained what dispersion relation is yet, but Scotia Theorem, you have the integral over the discontinuity, and you have the partial wave expansion inside the integral. So naively, we differentiate the amplitudes. We have a dispersive integrals, and we have a derivative outside. So he first argued that you can pull this derivative inside. Then he acted with the derivative on each Legendre. And then he used the properties of partial waves and these Legendres to bound this derivative. So the key step is really unitarity. I would say physics-wise, he managed to start with dispersion relations, which was used just QFT. And then he managed to, start dropping the derivatives, and he used unitarity to argue that what you get is, in fact, a convergence. So, so the miracle is unitarity, I think. Now, exactly which mass theorems he used, he has, I put again the note, he has the lecture notes, physics lecture notes, where he goes over this argument. So that's I think that's the best source to check for the details, but that's my understanding of the basic idea. I don't know if it's a satisfactory answer.
Well, again, thanks.
Okay.
Sorry, I just had, so you started by assuming polynomial boundedness, and then you've come to the conclusion that n must be smaller than 2. So,
yes.
So that does say something about the kind of theories that you're looking at, that
Well, the claim is that any relativistic unitary QFT has n less or equals than 2.
And the physical intuition behind that?
Well, there are, I guess, the basic physical intuition is that if S is larger than 2, you might violate causality. If you,
but you only needed exponential bound, right?
Sorry?
You needed just
yeah.
Well,
you can try to imagine the following experiment. Imagine you can, well, this is now not rigorous, but I give you an intuition. Let's say you have an amplitude which grows faster than a square. So you arrange for a collision. Then you arrange for a second collision from this particle. Then you arrange a second collision, another collision. Now, if S is larger than 2, you can arrange the wave packets that somehow you will get a Shapiro advance everywhere, and then you might try to turn it into violation of causality. In gravity, well, you will get something here which that's one way why it cannot be larger than S2 if you can accumulate it like that. Now in gravity it can be larger than S2, in fact, in quantum gravity. So it's something. Well, it's somehow the statement that relativistic objects. Maybe one intuition is exactly the model I gave you. So a model I gave you last time was that if you have a relativistic scattering and you look at how things scatter at finite impact parameter, you have a Yukawa potential, say some m star, and you have some amplitude which depends on S polynomially. So this gives you, if you are SR bound and you have Rho bound, unitarity gives you n equals 2. So yeah, somehow there is this fundamental fact that n is less than equal than 2, and then everything makes sense. You don't run into trouble, and all kinds of reasonable toy models work. But there is this, yes, there is this fundamental fact, and it will not be true always in gravity, for example. If you take a 6-dimensional gravity, I think you can get larger than 2.
I see. So can you impose any bounds, maybe less rigorous, on theories of massless particle gravity?
Yes. You can, but you do not have this argument. But you can run the arguments, the kind of toy model arguments from last time, using the fact that we have classical GR at large impact parameters. But this argument goes out of window because the crucial thing was that T was positive and finite, and this is just not true in theories with massless particles. So okay, so to recap, one thing that you should remember is this bound. You can let me write it like this. Write it like this. I don't know. Should put here the imaginary part. Let me just. And okay, this is really how you see it written in the books. I'm writing it so that you recognize it, because in the so here what I relaxed this averaging, which we used, and I write sort of pointwise bound, which if you average, you will satisfy that bound. But okay, here I made an assumption that these things make sense pointwise. And the second fact from all these discussions is a fact that we, well, I will call it 2 subtractions. And I will discuss dispersion relation next time. But for now, 2 subtractions is a statement that as S goes to infinity, we have this bound. It's the same as this n less equals than 2 is equal to 0. T larger than less than 4 squared. So modular various subtleties which we can discuss. These are I think this is the 2 most fundamental facts which came out the whatever S matrix. Sorry? Yeah. This one, yeah, it cannot be true pointwise, but you take S to be large, and okay. Then if you assume there are no resonances, yes, but okay, the rigorous bar says this. But yeah, I agree. That's, you know, you can imagine a local bump. None of those general arguments can exclude local bumps, and resonance is a local bump. And yes, let me write another formula that maybe is less famous. So these two are very famous. There is another closely related formula, just so that it also I've written it. Yeah. Yeah, this requires extra work. So far from what I said, it kind of sounds plausible that this thing holds at t equals 0 or less than 0. But now I think exactly the same trickery. So there is a paper by Jean and Martin again, which claims to show it for t less than 4m squared. I think it's, I mean, there are no new ingredients. It's just unitarity, dispersion relations, and analyticity. There are and then it's just arguing that you can do certain things, but there is no extra ingredients. And yes, and if you write this, then you can use you can use also another property about Legendres. If you take a Legendre polynomial, y square root 1 minus pi 2j plus 1 cos theta. Again, if theta is between 0 and pi, this is true. And then you have the bound that for physical angles, again, it's should be true on average, I think, in some rigorous sense, but the way it's written in the papers, it's like this. So here the idea is that if you turn on angles in the partial waves, Legendre start oscillating, and they dump your amplitude further. So here the bound is S3/4 compared to linear in S. Oh, sorry, I'm confusing you. There should be S here. Remember that the relation was that imaginary part of t is S sigma tot. And we bounded sigma tot by log square. So there is this S here. So you see that at t equals 0, it's bounded by S log square. And for finite angles, it's S3/4. So this is just the expression of this intuitive fact that Legendre start oscillating, and you get a better bound. Yes, very good. So this is related to the yes, the question is, which is absolutely a right question, is that why is it I have here 2 and why I have here 1? And this fundamental, this is a consequence of the fundamental fact that, let me try to get it right, x dx is x squared over 2. So when we in fact insert this guy, we average with the x, and so we have this 1 over 2 here. And if you would remember my previous definition, this guy is ds s sigma tot. So this will be 2, and then when we integrate, we get just 1. So with this 1/2 cancels this 2, because effectively this log doesn't matter. And very good. Now here again, I'm confusing you, I guess, but this is from this definition. This is a sigma tot. So if you plug it here, then in the definition, we have this kind of integral, and we defined it like this. And so now we have s squared, 1 over s in front. It was my definition if you check. So this gives us s, and this factor 1/2 cancels this 2 and gives 1.
And in your derivation, there were many steps, but the final claim is that, for instance, if, I don't know, we look at the top formula,
Yeah.
if you divide the sigma, average by s log s squared and take s going to infinity limit, you get exactly pi over m squared?
This is a stronger claim than what I made. I just said that it's a bound, and you are saying that this bound has to be saturated.
Yeah, I'm asking, yeah.
Yes. I think we believe that it's the case, that it is saturated, but so we believe that for scattering of protons it will be saturated, but this hasn't been shown, and it's an open question to show that.
And the last question is, for instance, I also remember, seeing that kind of,
Yeah.
argument when you artificially introduce, inside some big L, and then you have this and that. But, in examples, okay, I've seen a couple of examples, different fields. It would be easier, not to do such assumption, but estimate sum using Euler-Maclaurin formula.
Mm-hmm.
And it would be just first term would be integral and then correction, and it's typically easier,
I think exactly that's what we had these discussions with Slava and Thibault last time about last lecture about the impact parameter representation. And I think what people call impact parameter representation is exactly the first term in the Euler-Maclaurin formula. So people go from the sum to the integral, whereas they interpret this sum over j as the integral over impact parameters between things. And then things become indeed easier. But so yes, you're absolutely right. That's how things get easier. So I was just being very, very careful. Yeah.
Can I ask a question?
Please.
Yeah, I haven't heard these claims before, but I personally would be very surprised if this bound that you derived would be saturated. For two reasons. First of all, even for like plain vanilla massive series, you made so many simplified assumptions when you massaged your sums. So it's hard to believe that you like never lost anything. And you estimated all low momentas exactly by 1, all low angular momenta.
Yes,
in any realistic theory, that's definitely not going to be satisfied. And the second reason is that you never use the fact that pi is at pseudo-Goldstone.
Very good point.
Which certainly will suppress the cross-section in a QCD case.
That's a good point. That's a good point. And for QCD, indeed, I think there was even recently a paper, I don't remember who was the author, where people exactly analyzed the question of saturating the Froissart bound due to the fact that pines are pseudo-Goldstone. But I remember that this, so in my notes there is a reference to a paper by Tolle-Demarsky on Froissart bound, and if you go to this paper, he cites this paper on this Froissart bound, and indeed this is correct. However, let me go back to the model I like, which no, I think you are right. Maybe that's a very crude model. So yes, maybe the best way, in fact, maybe I'll try to, for the next time, maybe I'll try to find a reference, but maybe the best way to do it is that we go to the models of holographic QCD, where we have an extra dimensions and we have some warped geometry, and then high energy scattering will be dominated by some black hole production at the horizon, and maybe people just estimated it. Maybe that's the best way to look for this. But okay, it's a good question. It's a good question. Let me think about it more carefully. Francesco?
Okay. No, I wanted to ask, what is the obstacle to have a fixed angle dispersion relation?
Yeah.
It doesn't appear to be polynomial boundness from this bound that you write here, right? Is it analyticity or?
Okay, I think. Sorry, before I answer, I just realized when I said I realized when I was answering previous question, when I say that Froissart bound will be saturated, we expect in QCD, I meant we expect to have log square. It's true the coefficient can be. It's a more subtle question, but I think everyone agrees that log square should be there. Now, for the fixed angle dispersion relations, I thought that we can discuss fixed angle dispersion relations for we can people definitely discuss dispersion relation for partial waves, right? So that's for sure, and there the problem. So let's try to discuss dispersion. If we do dispersion relation for partial waves, I think you can write them. Just we start with the definition of partial wave and we plug dispersion relation inside the thing, and we do the integral. But the problem would be, and this is what we discussed at the lecture number 1, that say partial waves and this amplitude, they have 2 cuts, and somehow when we work at fixed angle and as opposed to fixed t, we keep this cut, but we mess it up completely somehow. We do not have control over left cut, so this problem, I guess, is often it's a left cut problem, or I don't know how it's called, but in other words, by working with fixed t, we have a control over the left cut. And if you do partial waves, maybe you can do it, but you will then have a function, whereas this you will have unitarity, but here you will have no idea what's happening, and then it just becomes useless. I think that's the basic reason. So now I want to any other questions? Yes, it's a good point to take a break now, and I will continue with this. Remember when we were proving the Froissart bound, we started with a polynomial boundedness at some t0 larger than 0. So I would like to discuss a little bit what is the meaning of this thing physically, and I made a comment that's related to the size of your object. I just want to make it more precise and at the same time explain what people call anomalous thresholds. Okay, so let's continue. And let's discuss something which is called anomalous threshold. And I will explain next what it means. Usually it's presented in one way, and I will present it in the opposite way, because I think maybe it's more clear. Let me start with the following question. Let's say you have a, what does it mean that you have a particle and your particle probes some other particle, and what does it mean that, what do you mean that it say sees an object of size, of certain size? Because I will next to relate this T0 in the previous argument to the size of the object, but of course to do it I have to first say what does it mean. And well, let me consider the electromagnetic. Well, there is a gravitational size to the object, there is electromagnetic size to the object. Let me consider electromagnetic size of the object. For example, if you have an electron and you have a photon, and you interact with an electron, it's a point-like interaction. And the one way to formulate it is that, let's say I consider this what is known as a electromagnetic form factor, and the electromagnetic form factor is defined just by definition, is you take a particle, you insert an electromagnetic current, because that's how a photon couples to whatever your electron, and you consider this scattering, this matrix element. Now, to discuss the size of the object, let me take this q squared to be space-like. And I define the form factor to be the integral of this form factor. And then you plot this f as a function of r. You'll find how big is this object. Say for electron to leading order, this is just a constant, so you'll get a delta function at r equals 0, and that's what we mean by electron being point-like. However, more generally, we can have a next. Let's consider next layer of complexity. So photon will see electron as a point-like object. But let's now ask a question: how would electron see a positronium? So what is a positronium? It's a bound state of an electron and a positron, and it's neutral. So you will not interact directly like that, because electron was charged. But for the positronium, the relevant diagram is this one. So here you have some neutral object of mass m, whatever it is. Let's say it contains some electron-positron pair. And then you have the same diagram. And you see that the size, maybe it's not completely obvious from here, but in this formula, the size of the object is directly related to the analytic structure of this function. How do you see that? Well, let's take an example, which is if this form factor is something like, the famous formula would be something like q squared plus m squared, which is a massive propagator. Then you see that this expression, it has a pole when q is equal to im. And if you do this integral, you do it by deformation of the contour, and then you see that the leading behavior of this guy at large R is controlled by the singularity. In particular, the Fourier transform of this is famously will be the Yukawa potential. So it will behave like this, and so the object is behave 1 over m. So at this level of form factor, there is a relation between analyticity and the size of the object, which is just the fact that if you do the Fourier transform, it is controlled by the closest singularity. And this singularity could be, you see that from the point of view of this Q, we're considering scattering, but the singularity lives at complex Q. This is not what we usually discuss. That in the physical scattering, T is negative. But if you do, say, if you consider T, usually T is minus Q squared, and you set Q to be complex, you get positive T. So that's a basic moral, that when you start talking about positive T, if you want to imagine some physics, you should think really about the coordinate space, not the Fourier space. And then it becomes really physical. If you have a singularity at some point, it tells you that, in fact, the object is of size T. And if you know that the object is of certain size, you can immediately predict that no matter which diagrams we compute, you will get a non-analyticity starting at this point. I think it's very important to have this in mind when we start talking about anomalous thresholds and like that. Because usually this diagram, some complicated mathematical expressions, but anyhow. So that's a basic point. Now let me evaluate this diagram for you. This is a Feynman graph, which has the following expression. It's a function of little m, big M, and q. And it's equal to the following integral. And you do it like it's done in the, as usual. You introduce Feynman parameters. You have delta 1 minus sum over alpha I. And here you have the following integral. M square minus alpha 1 plus alpha 2, alpha 3, M square minus so this is the integral, and it's a messy integral in the sense that I don't know a good formula in. But there is a simple formula for the following object, and because we care about analytic structure in Q, if you take a derivative with respect to little m square of this f, in fact, you can easily compute it. And I insert the formula in the notes. And the formula has the following structure. It's q square minus 4m square plus m to the fourth. And here you have, well, I will not spend maybe writing it, but you have some factor, some log, minus some other factor, times some other log. And these things are functions of these variables, and you can stare at them. But the point here, the important point is that it looks like this expression has a pole. The location of this pole is this. And the first questions that you should ask, okay, is it a real pole or, I mean, it looks like a singularity, but it's not yet clear if it is. And indeed, there is an interesting story that that you find that it is only a singularity of this amplitude. It corresponds to a branch point of the original amplitude when m square is larger or equal than 2m squared. So this is an interesting relation. You see there is some square root. So when the mass is larger than square root, then you get this cut. And this thing is called anomalous threshold. Why is it called anomalous threshold? Because let's consider now, let's attach to this diagram a second half. Let's say there is a scattering of some electron, positron. And if you look at it in this channel, and we talked before about unitarity, we said, well, if you have a unitarity, you have a normal thresholds. Let me call this variable S. If you have a normal threshold, then you will have a cut when you can start producing these particles. So you will start producing the particles for S larger than 4m squared. And then, well, these things are called normal thresholds. And we have unitarity for them. So they're controlled by unitarity. Now, this thing, which is q squared, if we look at from this side, it's exactly S. You see that it's less than 4m squared. So it looks very strange at first sight, but it starts before you start producing. There is a cut, which starts before you can apply unitarity relation, because 4m squared, in fact, if you have, say, this, if you have these particles like this, it is the minimal energy you can imagine in this channel, but you have a cut which starts below. So there is no a priori unitarity relation that you can write. So what you learn from this diagram is that it's very easy to get singularities for which there is no obvious unitarity relation that control them. And that's why they're called anomalous. So anomalous refer to the fact that there is no obvious unitarity relations that you can write. Now, let's understand what happened. I told you before that we expect that the closer, say here, if you have a singularity, so this minus q squared, it's minus s. If you have singularity starting at m, it corresponds to the object of size 1 over m. So if you have singularity which is closer than 4m squared, it means that this object looks bigger than just in coordinate space than naively E2mr. Now, there is nothing wrong about it. Why? Because we are familiar with such phenomena, and okay, this is a relativistic process. Let me consider a non-relativistic example of this type. What would be a non-relativistic example? Remember, we started, let's consider this particle to be a positronium. What is a positronium? It's bound states of electron and a positron, and it has some bound energy which we can compute using Schrödinger equation. And it's essentially the same as a hydrogen atom. And this bound state energy is much smaller than m. That's why it's a non-relativistic state. And clearly, if m is larger than square root 2 of m, we have anomalous threshold. Here, m is larger than 2m. Well, we can neglect that. So clearly, there will be anomalous threshold. So we know that if we consider scattering of positroniums, we will have an anomalous threshold. Now, for this object, because it's a non-relativistic object, we know, let's compute for this relation where the singularity is. You just plug it in this formula, and you get the singularity is at s equal 16m En ps, where it says bound state of the positronium. And by this Fourier transform, I told you that if you have a singularity, and this is minus q squared, this translates to the size of the object, which is this. So we take a square root and we take an inverse. And this has a name in quantum mechanics. And its name is Bohr radius, because this is the size of this object. And if you solve for the positronium, you will find that this is precisely what Bohr radius is, up to some order 1 coefficient. And so you see that, of course, if you take as a loose state of two particles, which looks big, if you look at it with a photon, you will see that it's big. But now let's translate it to the language of amplitudes. You see that what it translates to, that you should start having a singularities which starts before 4m squared. And if you now remember about our derivation of the Froissart bound, so this becomes T naught. That's where the cut starts. And therefore, in the Froissart bound, instead of the pion, for the positronium, we will have Bohr radius. So we have pi a naught square times log square. So there are several things which I want to say about this. First, how it comes, let's consider all the external particle to be of the same mass. I told you that there is no anomalous threshold. Now, let's say we slowly increase the mass. I told you there is a new singularity. What happens? How it comes about? The answer is that if you have a normal threshold, and you take some parameter, in this case m, and you continue it, what happens is that, let's say it's a complex plane, and this is all we have. This is just one cut. What happens is you continue m, there is a cut which pops out from the second sheet, and it comes out and it just stretches all the way to here. So whatever it is. And the lesson, which immediate lesson from this to take is that if we start with something physical, say we know that for t negative, for t less than 0, there was no, if we write the unitarity relations, we understand what is a cut here. It's related to the production. It has a physical interpretation. But as soon as you continue away from the unitarity region, you have to be careful about what you get. You should not expect that you will get the simplest thing, because there is different physics that can control it. So, and when we will discuss further the Mandelstam representation, that's precisely what we will do. We will start with something from what we understand, and then we will continue. And then the question is, OK, how are we sure that no crazy stuff pops out from these cuts? So that's why analyticity, or when people go away from axiomatic analyticity, that's why it's tricky, because a priori you have to understand like why things do not these crazy things do not happen. And the second thing about this example is that I hope it's clear that there is nothing anomalous about anomalous threshold. It's completely physical. We know from the start that we can expect it. So it's not like when, at least it's true that when we prove axiomatic analyticity, we say at loss S we don't know what we don't understand what's happening. But I think, as far as I know, apart from this, there are some concrete physical mechanisms that would put it forward for singularities or something. But I think this nicely illustrates that you should be a bit careful when analytically continuing from unitarity, that there is a different physics. And in fact, this controls this kind of form factor singularity. So it's kind of, the interesting thing is that if you look here, so if you look in this region, the right way to look at the diagram is that you have a pair of particles which annihilates and forms something. But if you look at this region, the right picture is that electron scatters and probes this particle in this channel, what its size. So, and if you don't have this in mind, that in fact after you go from here to here, you should switch effectively the channel which you think. You might think, okay, there is nothing here. This is what I wanted to say about anomalous thresholds. This is a simple example where, and here also another one general lesson that people found, which does not have a very clear understanding. There is no systematic understanding of this. In one line, what happened here is that you see, as soon as you start getting external particles heavier, you start getting this anomalous thresholds. Imagine that we only have one particle in the theory which has mass m. Then there is no anomalous threshold. And this is what people found in the past, that it happens in different contexts, in different guises. It happens again and again, that to get into this complicated analytic phenomena, you somehow need these heavier particles. I don't have a good understanding of that, and I don't think they offer also a good understanding in the papers. But yes.
Weakly coupled limit?
Well, this is not what I want to say, because I just wanted to. This is a picture that works when I have a description. When I have a non-relativistic description, it matches to anomalous threshold. But in general, if you have some particle and you have some coupling, these particles can have nothing to do with each other at the level of some Schrodinger equations. But as soon as you have this vertex, you will have this diagram and you will have this phenomenon. So this phenomenon is more general. It's just if you see this formula, it looks very mysterious. It's a relativistic formula. Why does it start here? And this is the way you can connect it to something we understand. Very simple. That's all.
it's just said, if we give you this diagram, so if you just look at the diagram you consider,
yeah.
So you have this vertex which corresponds, strictly speaking, to this big M splitting into M's.
Yeah.
Now imagine we're looking for the amplitude of scattering of these two particles with mass M. Then if this big M exists, it should appear as a singularity in this channel of scattering of these two objects.
That's right.
So therefore, if I will add to this diagram full set of the diagram, just to have full set of the diagram which I would like to verify arithmetic, I will conclude finally that there is some kind of bound states which I would call M, and this state will appear singularity in the amplitude of scattering of two small L's.
I agree. Yes.
In that sense,
in this sense, it's
if you did know that there is this kind of the bound states, you would recognize that it exists, just looking for much larger class of the diagram, including scattering of particles.
Yeah, I agree. So maybe it is true that by doing this, you can say that indeed, if we invert this diagram and we consider scattering of two M's, then there should be a bound state in this other channel. So from this point of view, the answer to this question, should have been different.
I also have a question. Can you hear me?
Yes, yes.
Yeah, so the fact that I missed the point. So the fact that we got the Froissart bound and this reasonability, what does it tell us about the presence or absence of anomalous thresholds in scattering of protons?
Okay, good. So yes, the question is what's the connection to the first part, and about the Froissart bound of say protons. So yeah, the question in the language of my first part is that what is T naught for a given process, and my understanding is that if you have for certain processes, well, historically at least, this has been worked out. Say I took pions. There is a list of other processes for which this T naught is known, and it's simple for m pi squared. Now, there are some other processes like scattering of protons for which a priori you cannot run the argument because we do not have that analyticity. My understanding is that if you use this BAS, Bros-Epstein-Glaser domain, and you use dispersion relations, avoiding this region, and you use unitarity, you can still run the argument, but I will not be able from just on the fly write what is T naught for the proton scattering. I think again in this lecture notes by Martin, he discusses this precisely, like how do we generalize these two protons, and there is some expression for T naught. My connection, again, a simple-minded connection, which is not mathematically rigorous, with the first part is the following. Let's ask the question of a Froissart bound for the positronium. And so then, without going through any rigorous analysis, I wrote this formula. So, which follows just based on the simple fact that we have this cut, and it's very physical, and it will be there. And so in this case, I computed T naught based on some simple reasoning. Now, it's a good question. Try to reproduce it rigorously. That's the logic I had in mind. So it's an example where this T naught is not simple 4m pi square, but where we can understand what it means, and it has the meaning is simply this is a control this effective size of the object.
Okay, thanks.
Any other
questions? Actually, now I'm confused because somehow your argument seems to be saying that you excluded that in the 2 pion channel there is an anomalous threshold.
Yes. Yes.
But how was it excluded by your assumption? Why couldn't there be a bound state of? Okay, we know that for 2 pions don't have a bound state in QCD, but in some other imaginary theory, one could have thought that perhaps this is possible, and you're basically saying that it's impossible. There cannot be a bound state for 2 massless, or 2 particles which are the lightest particles in the theory.
Yes.
But that isn't this surprising?
The way you put it, it does sound surprising. I agree. Yeah, moreover, let's say we can consider a theory and just imagine that we couple to this theory a state which has a mass slightly less than 2m, just another particle. So then it will be a bound state for 2 pions, and I think that the honest answer to this question is that when I say yes, it's a lightest particle plus no bound state assumption, then there are no anomalous thresholds. So if there are bound states, we should just add them and take them into account. However, I consider this as a sort of definition of a theory. So it's a bound state. So this is not an anomalous threshold. You will just have a pole. It's a bound state. We can have them, but that's fine.
So you are implying that when Martin derived his result about analyticity, he somehow used somewhere the fact that there were no bound states.
Yes.
Which is
Yes,
natural.
because otherwise he would not have been able to prove that T is analytic up to 4m squared, because it would be analytic only up to the first bound state. Yeah, I think this is an interesting point indeed. So it's not just some. It's in fact should be very physical somewhere there.
Sounds good.
Okay, next I will. So this was a very concrete, again, concrete exercise with which I try to illustrate a few things. Now I want to do another very concrete exercise with which I will illustrate another set of things, and then I will finish for today. So the next concrete exercise which we will do, and this is, I think, also historically how it was done, is to look at what happens for this diagram. So this is, again, if I draw a Feynman diagram, it's a box diagram. And the idea, you should think about it, okay, we can compute Feynman diagrams, but non-perturbatively, what we are doing here, we are asking the following question. Imagine you have a theory where you have a particle, let's say of mass m, and then you have a bound state of exactly the same mass. So there is a pole at m, and then there is a, say, a 2-particle cut at 4m squared. So then you can imagine that if you consider an amplitude, 2 particles of this type going to 2 particles, and you take the first cut, you see it somewhere here. And then you have a unitarity relation, the disk as t 2 to 2 is equal to the integral t 2 to 2 times t 2 to 2. And then, because this is a function of t, and as we discussed, you have analyticity in some domain. So you just can start in this domain and continue this equation. And then as you continue this equation, well, what you see is that you know from right away that this T222 has this pole. So if you continue this equation and you somehow you start pinching this pole, you will get a potentially some singularity, and indeed that's what you happen. And this corresponds to the fact that you have these particles here. Now, this diagram, therefore, it's a toy model of a non-perturbative theory, which has two particle states. It has a bound state, and we are asking the following question. What is the consequence of unitarity in this 2 to 2 region when we continue t to positive values? And then in the non-perturbative theory, you will have this graph. You will have some non-perturbative vertices here, which you don't know. But the point is that, in fact, if you want to describe gross features like where the cut starts, it only cares that this is when this goes on shell, it's a particle of m squared. And when this goes on shell, it's a particle of m squared, and these are m squared. For example, if I want to use this graph as a toy model of QCD, well, I cannot because there is a pole, but let's say there is some other massive theory, then what I have in mind that these are not quarks. We are not drawing the diagram for quarks. This will be a diagram for pions. For example, to turn this diagram into something that happens to pions, it's very easy. You just add this, and then such a diagram actually. Sorry, let me draw it like this. If you add this diagram, say this is a legitimate diagram for understanding this toy model of unitarity for pion physics, because you take the first cut, you get 2 pions into 2 pions, and then this 2 pions has a 2 pion state in the other channel. And the toyness of this model is in the fact that instead of these non-perturbative vertices, we collapse them to a point, and we draw a Feynman vertex. So here, what I'm trying to just quickly explain is that when we want to discuss what are the consequences of unitarity for the scattering amplitudes, in fact, Feynman graphs offer us a great laboratory, because what they do, they implement unitarity perturbatively, but they have these essential ingredients. They know about all these unitarity relations, about their analytic continuations. And if we don't care about the explicit form of this function, but we only care about its analytic properties, it's perfect to lab to understand the analytic properties of non-perturbative amplitudes. Now, this graph, you can compute it. And it takes the following form. First, let me write a perturbative representation. It's again just a bunch of Feynman parameters. Sorry. Yeah, here I took all the masses to be equal, so I'm really looking at this graph. And so this is 1, 2, 3, 4, S channel, P channel, and if you introduce Feynman parameter for each propagator, you get this expression. Now this is a expression which you can compute. It's some messy function, but Mandelstam in his original paper found a very nice representation for this graph. The representation is the following. This representation of a perturbative box is called the Mandelstam representation. And you see it makes the analytic properties of the function, at least on what is called the principal sheet, manifest, because you have this function. Let me write it. It has a theta function in it. This is a theta function. So it has only support when s and t are both positive, larger than 4, and also they're larger than 4 to the 4th. And here you have st square root, and you have square root of this expression. Okay, now what happened here? Something interesting has happened. First of all, if you draw this, so this rho is called a double discontinuity of the amplitude, or d-disk, or double spectral density, or Mandelstam spectral density. It doesn't matter. Why is it a double disk? Well, let's take a discontinuity in S. You just turn this guy into delta function. Then you take discontinuity in T. You turn this into delta function. So you get the d-disk of I is given by rho. So the double discontinuity is given by this rho. Now, the second interesting feature of this is the following. So you see all this, all these details here. What is the dependence on S on T, and this square root? This is a Feynman diagram. And if we are doing non-perturbative bootstrap, we don't care about that. Because, okay, this has the details about this vertex. You put another vertex, you will get something else. However, it has this theta function here. And if you think about the origin of this theta function, it is non-perturbative. It comes from the fact that you have a unitarity in this channel and you have a unitarity in this channel. And if you plot it on the curve, say S and T, start from 4m square. This is curve something like this. And the double spectral density is supported here. So this curve along which the scattering amplitudes, well, originally Feynman graphs developed double disk, is called Landau curve, because it was Landau who first understood how to find this curve, systematically. And the idea, how do you find this curve systematically? Well, you solve what is known as Landau equations. The idea is that you see that this double disk, well, it has a branch point, so it's some kind of non-analyticity. And if you think about Feynman graphs as a complex integrals with some contour, the only way such complex integral can develop, well, one way is the typical way how it can develop a singularity is if this contour is pinched by two poles. Why? Because let's say it's not pinched, you have one pole here, another pole there, and they move like this. Well, you just deform the contour and you do not have a singularity. So Landau equations, these are the conditions for the pinch of Feynman graphs, of a Feynman graph. This is a perturbative definition, but non-perturbatively you expect that these are the conditions, these are the pinches of unitarity kernels. So I think that well, it's clear that S matrix and scattering amplitudes, it's a story about unitarity. So, and when we have this unitarity relations, we can continue them, and then we can ask, based on the fact that these amplitudes have some regional analyticity and some set of cuts, what happens to this integral? And you see that it develops pinches, and it develops pinches exactly where you have this Landau singularities, and it's all match. It's not a theorem, so I have to emphasize that this is a rigorous fact. It's a Landau equations. He just analyzed the singularities of Feynman graphs, and this is in red. It's an interpretation that I attached to it, which I think is correct, and we have, well, all perturbation theory is evidence for that, and by construction, it's clear that I think there were even papers in the old days also just saying that that's why people who care about S-matrix theories, they cared about graphs because of this connection. Now let me write down the Landau equations quickly. To write Landau equations, you just in general, you understand that every Feynman graph, doesn't matter how many loops, it will have the same structure. It will be of the type that you have some after you do the integral over the loop momenta, you will have this Feynman parameters, then some numerator, let's ignore it, and then you'll have some denominator to some power, and this denominator, it depends on the Feynman graph. For example, here, this denominator looks like this. And you see, say, this, I don't know what's the right name for 2 trees in graph theory, but you see that, say, S, if you do the S cut, you cross the edge 1 and 3, so you get alpha 1, alpha 3, T, alpha 2, 4, and then for M squared, there is also some rule. So there is some rule where you can write this D. And then the condition for the pinch is the condition that in each integral alpha I, you have a situation where you have this integral from 0 to 1, and you want to have 2 poles. So these are the conditions, and you can check. So you have, it means that you have a, if these are the poles, for D, it means it's a double zero. So you want to have a double zero in every alpha I parameter, and in fact, you just see that it becomes this equation D for the alpha equals to 0. So, in fact, these polynomials D are homogeneous in alpha. You can I simplified it a bit here, but there is a delta function 1 minus sum of alpha 1 plus alpha 2, alpha 3, and alpha 4. And then you can rewrite this 1 as a square of the sum. So it's a homogeneous in alpha. So if you solve this equation, this is automatic. So you should really just solve this D alpha equals to 0. And you want the pinch to be, for this to develop a singularity, at least if we start with this contour, you want this alpha i's at the pinch to be between 0 and 1. Because otherwise, if you pinch somewhere else, your integral will not be singular. So now, this is the basic story. And what people did in the past is that they try to understand, OK, so let's use this as a guidance and try to understand what are the analytic properties of the amplitude at SNT as a consequence of unitarity, because by studying these diagrams. And the simplest option, which was offered right away and was based on this one loop diagram, is that if you take a non-perturbative amplitude, you can write it like this. This is known as a Mandelstam representation. And this hasn't been proven, but it's why not? Because it's hard, and what happens is that it's okay, based on our triangle intuition, you can already make a hypothesis. And the hypothesis would be the following, that if we consider a scattering of particles, let's take the same graph and make these particles here m, and the external guys to be large m. So what happens as this is a nice formula when they were equal. Let's take m and start increasing it. And this is a question that Mandelstam asked in his paper. And he found that, well, crazy things start happening. So first of all, this region, it gets deformed, it develops some bulges, then it develops some cusps, and finally you start getting some complex singularities. So this representation breaks down. So in fact, very quickly, as you increase your m, and the mechanism for this, I believe, is the same that we had for anomalous threshold. As we continue in m, new things start coming out from the second sheet, and they populate the physical sheet and start making things very complicated. And in particular, so okay, the fact that you have a formula where instead of this shape you have some boundary shapes which is more complicated, it's not a problem. Okay, well, you just put a different region, that's fine. But what happens is that after you increase m a little bit, it's just you start having what's known as a complex singularity. So, which is that here you see that all the double disk is contained for real S and T. But what happens is that if you continue m, you start getting some cuts in a complex plane. So, and then if you start getting these cuts, it's really becomes a wild, wild west, and not very little is known about these complex singularities. And at first, people thought that okay, maybe that's maybe this is some nuisance, but we can do without it. But then, anyhow, they start finding more and more examples of this singularities. There is this thing. Yes, so the original attempt was to prove Mandelstam representation perturbation theory by recursion. You start with some region of analyticity. Maybe you know that there are no anomalous threshold. It's for some diagram, for some box. And then you try to run some recursion. It's a smart recursion. And then you try to establish Mandelstam representation. And part of this recursion was based on the fact that some complex singularities do not happen. And then in 1 year, people found this, well, there is this famous about this. This graph is called Ecknode graph. People analyzed this Ecknode graph, and they found that there are complex singularities, and so it invalidated the proof, and the subject was abandoned, essentially. However, one way, I think, and I think that's why that's where we are more or less now. But there is one hypothesis which emerged from this analysis, which we can call the lightest particle maximal analyticity, which states that if you consider a scattering of lightest particles plus no bound states, then the analyticity of the non-perturbative amplitude is the same as analyticity of Mandelstam representation, which is that you just have the simple cuts, just normal thresholds in both S and T. And so I think this is the simplest statement that came out of a lot of complicated analysis. And this is a hypothesis which, as far as I know, it hasn't been, of course, hasn't been proven, neither perturbatively nor non-perturbatively. but also it hasn't been disproved.
So if you're trying to do, say, S-matrix bootstrap, does this mean that you're basically constrained to only consider the S-matrix for the lightest particles? Because
it depends what you want to assume. Yeah, it depends. If you want to assume maximal analyticity, then yes. If you don't want,
is the loss of analyticity that you have in scattering heavier particles controllable?
No. It's controllable. That so there is this region, axiomatic region of analyticity that we discussed last time, and which I used in the proof of Rossar bound. If you stay there, it's fine. You see that this formula allows to take you take S whatever you want, and you do not restrict yourself with t less than t0. It allows you to go to any t. So it's a way more powerful. And so if you restrict yourself to this axiomatic analyticity region, you are fine. But if you want to go beyond, then this is a formula, and I think it's it's very interesting question to understand. I want to make maybe a couple of comments here. First, it's why is it a non-trivial statement? For example, why is it surprising that something like this is true? Because I told you that if I take a graph, a box graph, where the external particles are not the same mass, then you start seeing this crazy phenomenon. But then you see, let's take this graph. So now you have this subgraph. And for the purposes of Landau equations, all particles go on shell. And then this effectively describes a particle of mass 2m, 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 and this is a particle of mass m. So for this box inside this larger box, there is no way you will have Mandelstam representation. But somehow the idea is that if you embed this box into a larger diagram where the external guys are light, this should become harmless. So at least this is a conjecture, and it would. Now the second comment, which is I guess obvious. So I think it's very important to understand this better and to understand if this is true, even in perturbation theory, and somehow not much work has been done. So I hope we will have some progress on that. And the second point which I would like to make is that, remember at the beginning of the second lecture, I told you that if you are doing a S-matrix bootstrap, then your tools, or depending on which your power depends, is how much analyticity you have. And so if you assume more analyticity, then you have more power. And in particular, you can derive stronger bounds. Say, I wrote to you this bound on the fixed angle scattering in the first part. And if you assume Mandelstam representation, you can make it stronger. So the idea is, therefore, it's not just some academic exercise whether Mandelstam representation is correct or not. But in principle, we should derive all the bounds that follow from the Mandelstam representation and say applied to the experimental data of pions. Then if you see that the pions violate this bounds you derived using Mandelstam representation, you have shown that non-perturbative Mandelstam representation does not hold. So there is a perturbative part to it, which is that we should understand how it works at the level of diagrams. But there is also a non-perturbative part to it. Let's assume it derive all the bounds and confront them with the experiment. And my understanding, well, I'm not sure if anyone has done it really carefully, but my understanding is that it has not been ruled out. So it's still a possibility that the scattering of pions is described by formula like that. Yeah. And another little comment, but it will be much more technical, which I would like to make, is the following. So if you write Landau equations, for this graph. So let's differentiate, say, with alpha 1 and alpha 3, etc. And you can also, in fact, for these Landau equations, you can impose the symmetry of the graph if all masses are equal. So you get something like say t minus 4m squared. Okay, I switched some notation, but it doesn't really matter, so I hope it's fine. So this is the derivative with respect to, I guess, alpha 1 set to 0. Then there is the second equation is like this. And so the typical, and this is always the case, you get Landau equations where you have say external variables being s and t. You have alpha 3 and alpha 4, and it's a homogeneous system, so it has only solution when the determinant is 0. And this 0 determinant gives you the equations for the Landau curve. Now, so far we discussed the Landau curve for the real axis, and we got this Mandelstam representation. But in principle, if you think about s and t as complex variables, this is a C1 inside C2, right? This is a complex equation, and so we have some complex surface. Now let's try to see where the surface goes in the complex s and t domain. And if we take s and t, say, to be real somewhere here, and we try to ask where the complex surface goes, we can add to say s a little bit of imaginary part, and we add to t a little bit of imaginary part, and see where the how to satisfy the equation. And you see that you will get im s plus im t equals to 0. So therefore, that to satisfy the equation, the imaginary part of s and imaginary part of t will have a different sign. So this is how you can satisfy this equation in this region. And therefore, it looks like, imagine you found some pinch, you found some Landau surface, and then you follow this Landau surface into the complex plane. Then, if it has been singular from this direction, then it sounds very dangerous, because let's say we approach in the s plane from above. So we take this equation and we analytically continue s from above, and we continue t from below. So if this is singular, then you just go back, and it looks to you that, and you will get that you will have a singularity in the all complex domain. But you know that this doesn't happen from this formula. So therefore, just based on this equation and this simple picture, you know that if you take this integral and if you approach it from this direction, so s, say, from the plus, from above, is plus, and this is from the minus, then this should be regular. But if you take this box, but I told you that this box has a singularity, as a branch point. Therefore, you will conclude that this branch point appears for I++ is singular, but it does not part of this complex Landau surface. I guess in the old days they called it virtual singularity, but doesn't matter. But there is this interesting fact. There is this interesting fact about this just one loop box, and it has a very physical interpretation in terms of the shape of the complex Landau curve. So this is a prediction, and then I inserted an explicit computation in the notes where you can check that it's indeed the case. So it is consistent. I think I will probably stop here, and I will continue next time with dispersion relations.
Any quick questions from the audience?
We can take a few minutes, Monica. So it should not be quick. It doesn't have to be quick.
How does the Landau curve look like in the Mann-Stam triangle diagram?
Yeah, normally, okay, so. So I guess this is the S channel, physical S channel. This is physical T channel, physical U channel, and I guess we will have something like this. So it's asymptotic to this normal threshold, but it lies in the unphysical channel. So you do not. These Landau curves, they do not interact. So if you measure this in the experiment, you do not see them. So here you see that the physical experiment is S large, T negative, but it starts for T larger than 4m squared. So.
No questions? Also from the online people?
Okay. So can I ask, is this story completely trivial in 2D? For example, lightest particle maximal analyticity, or even there it's something interesting to.
Yeah, in 2D, one big difference is that in 2D there is no T, there is no angle. So it's just a function of one variable. And so this whole story immediately collapses in this sense. And then so it becomes a question about I think in 2D, the fact that in the upper half plane and the lower half plane you do not have anything, then you can have some bound states. I'm not sure you can have anomalous thresholds in 2D. My guess would be no. So to first approximation, modulo some forgotten subtleties, I would say yes, it becomes trivial in 2D.
Yeah, just to say that there are some anomalous thresholds, but I think there are poles. There would be poles on the real.
Is there a cut, or I thought
no,
there are this Coleman-Tan poles, whatever? Yeah. Thank you.
No questions?
What about this Mandelstam representation for massless particles, dimensional regularized theory?
So yes, let me since you asked, I would like to make another comment about this, because there are two things which go into Mandelstam representation. One is maximal analyticity, and this you can control with a Landau equation, but there is a second ingredient which we have no idea about, and there is really no clue, which is that if we take a discontinuity of the amplitude, so then let's say we take discontinuity in S, so we kill one of the integrals, then this formula looks like a Cauchy integral, a representation of something in terms of its discontinuity. And so for this to be true, that discontinuity has to be, say, polynomially bounded in T, disk in S, should be polynomially bounded in T for any S, and this we don't know. In particular, I really would like to know anything about this question, but because if it's not a polynomially bounded for any S, you will never be able to write such a formula. So, and there is really, at least I'm not aware of any argument, even non-rigorous intuitive, any argument which would say that this is true. So I think that's an important point. And the same question will arise for massless particles. Say for, in fact, when we looked at the, yes, one comment. If you look at the large NQCD, with Amit, Zohar, and Simon, we wrote this paper about the disk in a large NQCD in exactly in this region, and we found that it grows exponential at large n. So in fact, it violates that. But this is a large n analysis. Here we're asking a finite n. Now, I don't know what happens in theories with massless particles, especially in gravitational theories in this region. I just have no idea. Now, if you say Mandelstam representation in terms of just the region of analyticity, that there are the simple cuts and nothing else. Yeah, it would be interesting to understand if one can argue for that even in perturbation theory. Well, we can do dimensional regularization. We just simply can consider theories in, say, 5 dimensions or higher, and ask what happens there. Again, at least I'm not aware of statements that it does not hold. Maybe someone knows, so maybe it does. I think we just don't know. Yeah.
Any other question?
Well, one comment is that so there was a work by Pedro, Joao, Balt, Miguel, where they assume this lightest particle maximal analyticity, and then they did some bootstrap, and then they did bootstrap with assuming Mandelstam representation and not, and they got the same, but in fact, since the amplitudes were polynomially bounded anyway, presumably it doesn't make a difference. So yeah, sorry, ignore the comment. It was.
Happy note. Let's thank Sasha again.
Yeah.